Hi folks. So since we have another snow day, I'm going to make some videos for you to talk about Module 13. Hopefully I can lecture through most of Module 13 so we can do a couple of experiments next week and you'll be ready for that. Make sure that you do the two assignments I emailed you. First is Lab 12.1, which is to use the data that we got during Lab 6.1 to do some gas law calculations. So you have the calculation sheet. I think not a lab report, but just, it may say write a full lab report, but if you can just do the calculations and get them right and turn them in, that'd be great. And I sent you the data that maybe you didn't necessarily get from Lab 6.1, so that if we all use the exact same data, each lab group may have been a little different. If we all use the same data, then it'll be easier for us to compare answers. So I sent you temperature, pressure, and the circumference of the balloon from which you can calculate the volume of carbon dioxide gas generated. The second assignment was to use Bond energies and Hess's law, both two ways to calculate the change in enthalpy for the reaction of the combustion of methane gas. And one of the videos that I do today will show you that, but please try to do the work first before you watch the video for that, just so you can check yourself. I'll also go through lots of practice problems on the videos so we don't have to use class time for that, and we can use it for experiments and questions. Make sure you are well prepared for class next week. Lots of the topics that we cover in Module 13 are new, and the concepts are somewhat different than what you're used to. So I'm going to start with enthalpy. Enthalpy is basically the amount of energy stored in the chemical bonds of a substance. You all know that when you have a chemical reaction, bonds in the different chemicals break and new bonds form. So the reactants break apart their bonds, and the products are formed when new bonds form between different atoms. The reactants have energy stored in their chemical bonds, which is liberated when they're broken, and then the products will also have energy stored in their chemical bonds. So when you talk about enthalpy, usually we're not going to be able to measure the amount of energy per se as much as the change in enthalpy from one kind of thing to another. So as probably a lot of you know from some of the other things we've done, like we've looked at delta T, which always means change in temperature. Delta H is going to mean change in enthalpy. H is always the variable that we use to denote enthalpy. Okay, so delta H, change in enthalpy. Enthalpy. Remember that enthalpy is energy stored in chemical bonds. There are two ways to calculate the change in enthalpy for a reaction. One is by using bond energies. This is the least accurate way to do it, although there's not a giant difference. And when you do that, when you use bond energy to find the change in enthalpy, you have to first write a balanced chemical equation. Then you have to draw Lewis structures for every single reactant and product. Also, just like we talked about during Module 12 with gas laws, the phase of each reactant and each product is now going to be very important. So is it gas, is it liquid, solid, or aqueous? And these things really matter at this point in the year. So whenever you write a balanced equation, you must include the phase for each substance. So, two equations about enthalpy that are really important for you this year. The one for bond energies. This equation is very different from all the other equations that you'll use in this module. So when you do bond energies, just think This equation is different. The others are all the other way. So for bond energies, and I'll even look to make sure I write it down correctly. Let's see, bond energies. Right, super great, didn't have it there. So when I do bond energies, it will be change in enthalpy is the change in enthalpy of reactants. That delta didn't come up very good. Minus the change in enthalpy of products. Just for bond energies. It'll, my pen. It'll always be the opposite way. Products minus reactants for everything else you do. So bond energies is just backward. The other important equation for enthalpy is Hess's law. Hess's law. Now Hess's law can be stated this way. Let's see. Change in enthalpy, or delta H, is a state function. Well, that doesn't really tell you a whole lot, does it? But this is really not as complicated as it might seem. So a state function is just something that is independent of path. So another way you could say that is independent of path. Well, what does that mean? What it basically means is whether I produce a water molecule by, say, an acid-base reaction, we could say HCl plus NaOH, and of course you all know that acid plus base gives you salt plus water, so sodium chloride plus water. Whether I form my water this way, of course that would form a liquid water, right, because phase is important now, or whether I produce water from the combustion of hydrogen, H2, of course gas, plus O2 gas gives us H2O, and of course I would need to balance it, gas. So if I formed water this way, and then I formed water this way, here's the caveat, as long as I got them to the same temperature and pressure, if I got all their conditions the same, if I got this water and this water to the same condition, then they would have the same enthalpy. They would have the same amount of energy stored in their chemical bonds because they're water. It doesn't matter how they became water. It just matters that now they're water. So as long as they're brought to the same condition once they're water, same temperature, same pressure, they'll have the same amount of energy. It doesn't matter how they were formed, whether this way or that way or some other way. As long as they're at the same temperature, pressure, all conditions being the same, then they will have the same enthalpy. Hess's law says that enthalpy is a state function. So just doesn't matter about the path. I sent you an email with a couple more examples. I think your textbook gives examples, things that are independent of path. Maybe I'll give you one more just to be safe. Okay, so remember H is enthalpy. So let's say, I dropped my pen. Let's say I go from point A to point B. I could go that way, or I could go that way, right? Regardless of the path that I take, I start at point A, I go to point B. Regardless of path, I get to the point B in the end. So regardless of the path I take, I get there. That's like a state function. Going from point A to point B is a state function. It doesn't matter what path I take. So, enthalpy. Energy stored in chemical bonds. So then, partly something that confuses some students, I'll put H back, enthalpy. Then we'll talk about S, no reason to call it S, but this is entropy, which these two words seem similar, very, very different. S will denote entropy. Entropy is the amount of disorder in a system. And so the second law of thermodynamics says that entropy in universe must stay the same or increase. You cannot have a net decrease in entropy in the universe. Now, you can have entropy decrease in a given area. For example, let's turn around and look for a minute. See that? Entropy. Big mess. So if, I'll get us aimed back here again. Okay. So if I went and cleaned all that up, disorder would decrease. Well, does that violate the second law of thermodynamics? Why, no, it doesn't. Because as I clean up, even though disorder decreases in the Lego mess, you would have me breathing, me burning calories, me heating up the air molecules as I move through the room, and the net amount of disorder would actually increase even though I cleaned up the mess, and it would look more orderly. So the second law of thermodynamics is just that the universe will always either stay the same or become more and more disorderly. So S is entropy. The equation for Hess's law, change in enthalpy, and Hess's law uses this notation. Let me show you. So Hess's law says the change in enthalpy at standard conditions. See this tiny little, it looks like a degree mark, like degrees Celsius. This little mark here means standard conditions. That means a normal lab. Normal lab's going to be about 25 degrees Celsius, which is a comfortable room temperature for people, and 1.00 atmospheres of pressure, which is pretty much what we hope to have, in a room. So when you do this, you need to use, of course, Kelvin. So that'll be 298 Kelvin for standard conditions. Last week we talked about standard temperature and pressure, STP, which is 0 Celsius or 273 Kelvin and 1 atmosphere. So don't be fooled. And also when you're doing problems, if you know you're at standard conditions, don't forget that you know this information. You know temperature and you know pressure. So even if they don't directly say, if you're at standard conditions, denoted by this little degree symbol, then you know temperature and you know pressure. And make sure you don't confuse it with standard temperature and pressure. Standard conditions are room temperature, not freezing cold 0 degrees Celsius. Okay, so Hess's law says that change in enthalpy at standard conditions is going to be the change in enthalpy of the reactants minus change in enthalpy of the products. Note that that is backward from the way bond energies are done, but this, a restatement of Hess's law right here, is normal for all the other equations. Similarly, the equation that you can use for entropy is change in entropy of reactants minus change in entropy of products. So very easy. You guys also do, I think, Gibbs free energy. So let me tell you a little bit about Gibbs free energy. So luckily, even though H doesn't look anything like enthalpy and S doesn't look anything like entropy, at least Gibbs free energy is going to be denoted by a G. So yay. Gibbs free energy is useful because you can calculate it to determine if a reaction will actually happen or not. And so it can save you a lot of money in the lab because you can just do a quick mathematical calculation to find out if anything will actually happen if you mix all this stuff together before you spend the money on the chemicals to actually do it, and then nothing happens. So when Gibbs is a negative number, the reaction will be spontaneous, meaning something will actually happen. So negative Gibbs free energy equals reaction actually happens. If Gibbs is positive, then the reaction will not be spontaneous under the conditions that you're assuming. So mixing that stuff together will be a waste of your time and money. Don't do it. So that's why you want to find out about Gibbs, why you need to know. The equation for Gibbs is just the same as these two, and there's also one more. So you could calculate Gibbs this way. You can do, I have a chart here. Here we go. Yes. So I'll give you next week, you have all these tables in your book, but I'll give you one of these for the test. It says OK for test, so your mothers know you may use it. And it will have lots of numbers that you may or may not need on the test. But Gibbs is given here, and you can use the chart, same exact equation to find it. So one more equation though, to calculate Gibbs and relate it to entropy and enthalpy is this. And make sure you memorize these. I'm writing them down just to make sure that you memorize them for the test. So Gibbs is going to be the change in enthalpy minus temperature, it must be in Kelvin, times entropy. So you can do this. There are a couple of really tough problems in your practice problems this week using these. So Gibbs free energy just tells us, will this reaction actually occur? If it's negative, it will. If it's positive, you need to change your conditions before you waste the money and chemicals time. So I'll stop this video so it can upload kind of faster, and we'll come back with, make sure you do the work before you watch the video. We'll come back using bond energies and then Hess's law to do the same calculation to find the change in enthalpy for the combustion of methane. I sent you an email with that problem, the 4 parts that I want you to do. So go ahead and do that, then come back and watch the next video.